What's up, guys? We are now in problem number 42, chapter 6, multiple phase mass balance. And I like this mass balance because it's going to have a lot of concepts we can analyze. So nitric acid is used extensively for the production of inorganic and organic nitrates, for metal treatment of various kinds, and for photo engraving. It is produced by oxidizing ammonia to nitric oxide over a platinum-rhodium catalyst, oxidizing the nitric oxide to nitrogen dioxide, and dissolving the NO2 in water. Essentially, we have these three reactions. And there is also a side reaction that lowers the product yield, which is the oxidation of ammonia. So here's it. Number 4. We don't like this side reaction. So the process goes as here. Saturated ammonia vapor produced by vaporizing pure liquid ammonia, so it's pure liquid ammonia, at 820 kilopascals, the pressure is absolute, is mixed with a stoichiometry quantity of air. So this is the stoichiometry of air, so you have all the oxygen you need. And the combined stream enters a converter, which is here. Prior to being mixed with the ammonia, the air is compressed and passed through a preheater. It enters the compressor at 30 Celsius and leaves at 1 atmosphere. And 1 atmosphere is also the inlet, with a relative humidity of 50%. So all these conditions are here. It exchanges heat in the preheater with the gases emerging from the converter. The quantity of oxygen in the feed is the amount theoretically required to convert all the ammonia to nitric acid. In the converter, the ammonia reacts completely with 97%, forming NO, which is this. 97 goes to here. And the balance formation N2, which is this 3%. Okay. In the short time in which the reaction mixture is in the presence of the catalyst, so they give you this time, I don't think we're going to use it, a negligible amount of NO2 is formed, so here. The product gas is subject to a series of cooling and hydration steps in which the NO is completely oxidized to NO2, which in turn combines the water, some of which is present in the product gas, the rest is added, to form this mixture 55% aqueous nitric acid solution. So probably that's the final specification. The NO formed in the later reaction is reoxidized and then added to the NO2. Okay, the product gas from the processes may be taken as only N2 and O2. So they give you this simplified process chart, which is cool, it's nice. You have the inlet, you have the preheat air, the converter, the products, you have air here, the preheater, then they go to the cooling and hydration. I love it because instead of using all the equipments, they just give you like this black box in which you cool and hydrate everything. And yeah, essentially they are going to ask us letter A, taking a basis of 100 mole of ammonia. So this is 100 mole of ammonia. Calculate first the volume of cubic meter of the ammonia vapor, so this vapor, the volumetric flow, and the air to the feed process of this, using the compressibility factor equation for ammonia. So this needs to be real, and this is going to be modeled as ideal gas. Now, letter number 2, the moles and molar composition of the gas leaving the converter. So essentially this here, moles and composition. The moles and molar composition of the gas leaving the converter. Okay, I think it's, what's the difference? No, it's just what I said. And 3, the required feed of liquid water, which I think is mass. I don't know, they wanted the cubic meters. Essentially you just need the density here. And yeah, essentially that's what they're asking us. Be real here, the inlet, the ideal gas calculation of the air, and the moles here, and at the end they want the amount of water needed to do that. So I'm going to write you the strategy, just wait for it. What else do we have? Then they'll tell you letter B scale this. Well, once we have everything, scale to a basis of 1,000 metric tons of the nitric acid. So first we got this basis number 1. Now basis number 2 will be 1,000 metric tons of this product. But yeah, that's the easy part. When we finish, we're just going to calculate the conversion factor and do all the conversions at the end. So let me just write this diagram here so you can understand what we're going to do. Okay, this is our mixing point, then goes here and then mixes here, and then goes to the preheater here. In the preheater we're going to mix air. This is air at 1 atmosphere, 30 Celsius. I'm going to, well, let me add everything later. And here, got this here. This is water, and I'm going to take out N2 here, O2. What else? Well, I have the product, which is HNO3 at 50% mass. And here I'm going to recycle this stream. Okay, the feed I'm going to use first is 100 mole of NH3 at saturation at this pressure, which is 820 kilopascals. Now the converter, I'm going to have also, let me go there, down here. This is N1 is the amount of O2 because it's oxygen, and I know in air I always got this 3.76 times the oxygen of nitrogen. And I'm going to have a little bit of water, so take that into consideration because it's actually, this is saturated at 50% relative humidity. Now I'm going to have the diagram states here. I'm going to have all these. So let me check, where do they ask me? The moles and molar composition of the gas leaving the converter. So it's here. Go here, and it's N3, N4, N5, and 6. So I have water, I have oxygen, I have nitrogen, I have, what else? Oh, of course, NO. Good. And now let me go further up. What else? Well, here, let me just do it. You don't know this, but N8 and N9, this is in moles, so I don't know it actually. This is water, and the balance is HNO3. Let's call this N7. I think I have all the numbers. 1, 2, where is 2? Oops, we don't have N2. Oh yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. I think we don't need more. We might use this N10 and N11. You wanted to. I don't think we're going to use it, but okay, we have our diagram. It's complete. The recycled, we're not going to use it because I don't think we are asked to, but if we need it, we just add a number here. Okay. Sorry. We're going to start with the strategy. So the strategy is as follows. We need the temperature of saturation. That's good because we know it's saturated here. So with this, what does that mean? It means that in saturation we can calculate the temperature by using Antoine equation. So we'll need the constants A, B, and C, and then we get T of saturation. Why do we need temperature? Because we will need it in our equation C and R, T divided by P. We got pressure, we got the constant here, we got the moles, and we essentially need the compressibility factor C and the temperature, which we got from Antoine. So C, once we get temperature, we can calculate the reduced temperature and the reduced pressure. With this we get C, and that's the only thing we need for this. C comes from chart, remember? And yeah, let's do it. It's very simple. This is the first part. The next strategy, I'm going to write it to you guys when we get to that part. Let's do this. Concentration of ammonia at I don't know which temperature. It's equal to 820 kilopascals. You could also go to tables and find it, or in the internet probably you just type this and they will show it to you. But we're going to use Antoine. And for that I need to change to millimeters of mercury. So I changed this, I got this amount of millimeters of mercury. And what else do I have to do? Okay, the Antoine equation, it's A, B, and C. I found them to be 7.55. B is okay, and this 247. So let's do this thing of Antoine equation. Remember, it's A, which is 7.55, minus B, which is 1002, divided by the temperature plus 247.9. And yeah, from here we can substitute this pressure, which is 6170 millimeters, and just find temperature. The temperature, let me calculate it, will be the logarithm here. It's this minus this, that multiplies this plus equals minus. So what else here? This here I got to be 3.75 times. This is 266.5 minus 247. This is just math, algebra. I got 18.6 Celsius. That's my temperature at saturation. Good. Now let's go for Z. Z is essentially a function of TR and PR. We will need critical pressure and temperatures, which is where are they? You got them here. It's 1, 4. No, this is 100.3 Kelvin, and PC is 405 critical pressure. So PR, oh sorry, it's backwards. It's TR, now TC it's 405 Kelvin, and PC it's 101.3 atmospheres. So TR it's essentially just the temperature divided by critical temperature. Yes, temperature we have, it's 18, so that's got this divided by TC 405, and I get 0.472. PR it's P divided by PC. The pressure we're operating is 1 atmosphere, I think. No, 820 kilopascals. Let's change that to atmospheres. 100.3 pascals. It's 1 atmosphere. Let's divide this by the pressure here, the critical pressure, and I get 0.07. So let me actually go for the table and paste it here. Give me this second. Here. We were looking 0.7, so I think let's find first the pressure, 0.07, and it's around 0.7 will be 0.1, waste 0.1. It's something about here. And the temperature, it's let's say it's like here. So I will add C equals 0.92. And yeah, essentially we got everything for our calculation. We need CnRT divided by P, which is the ideal gas just with the correction here. So let's substitute all the data. 92 moles is 100 moles. We choose that feed. R 8.314 cubic meters, pascals, mole, Kelvin. Temperature it's 18 plus 273. All these divided by pressure. Where's the pressure? It's 820 times 10 to the 3 pascals. My volume, it's volumetric flow, it's equal to 0.271 cubic meters of NH3. And yeah, that's the first letter A we need. They ask us also the one of air. Let's do the one of air. So for air, actually, I don't need that much of strategy, but let me show you the strategy anyways. The strategy is we need air or dry air, and water or moist water. This air, we're going to use it with stoichiometry. We're going to use stoichiometry from the reactions to know how much oxygen or mole of oxygen we need. And we know how much air is or with that oxygen. So we find the moles of air. This water, for the other side, we're going to use the one of relative humidity. With relative humidity, we calculate the amount of water. And with the amount of water, we go and just add up these guys. And we have our wet air. And then use ideal gas to get my volumetric. This is moles. This is volumetric flow of wet air. So let's do it. It's kind of easy. V of air equals, well, let's wait for it. We have this equation, NH3 plus 2O2 gives me HNO3 plus water. And therefore 1 mole of NH3 will give me 2 moles of O2, or not give me, will need to have 2 moles to react. So 100 mole of NH3 ammonia, it's going to be 200 moles of oxygen. It's what I need. So we got the amount of moles we need here. Let's change that to air. So 200 mole of oxygen is the total. I know 21% of that is oxygen. So therefore, how much will be the 100% if I wanted air? Let's do this calculation. This is moles of air. And that's around 952 moles of air. Now we are here. We cannot proceed. We need to go to the water info. So moles of water will be calculated from the humidity times vapor pressure of water at 30 Celsius. Take care about that. Divided by pressure. So the humidity is 50%. This pressure, I found it in books, 31.8 millimeters of Hg, divided by pressure, which is 760 millimeters of Hg. So this water, take care guys, we're not any longer here. We're not using this data. We're using these data. So let's get back. This number is equal to 0.02, and hopefully you know the definition of why the mole fraction of water is the amount of water divided by the amount of water and the moles of air. So I don't have this. I will need to calculate it. Moles of water divided by moles of water and dry air. I got it. It's essentially 952 moles. So solving this, you should get N of water equals 20 something, 20.36 moles of water. And yeah, essentially we need to add all the moles. So 952 plus those 20 moles, it's 972, I think, yeah, moles of air, or let's say wet air. And essentially, yeah, we can do this. Wet air equals the total amount of moles times the volume occupies 1 standard mole times the temperature, standard temperature. We have no changes in pressure, so this will be 0 or 1, sorry. The total moles is 972 moles. The volume it occupies is 22.4 liters per mole. Let me change that liter amount to cubic meters. Times temperature. What's the temperature? I think it's 30. Yeah, 30 plus 273 divided 0 plus 273, the standard one, and I got 24.2 cubic meters of air. That's also my answer, which is here. Air feed to the process using compressor. Okay. Number 2, the moles and molar composition of the gas leaving the converter. I was reading and I saw that probably, okay, we're going either this or this. So I think this is the correct one because you don't know the recycle. So yeah, we're going to calculate these ones. Go a little bit further here. Letter A, number 2, will be moles after converter. Yeah, essentially, let me go back just to be sure. Yeah, the strategy, let me show you the strategy we're going to use. It's essentially, we're going to use stoichiometry and that 97% of reaction to know how much moles of NO, which is N3, we're going to produce. Now with mass balance, we're going to find out how much air do we need, and then we do a mass balance again, and we find the amount of oxygen and nitrogen we have there, and then simultaneously we do the humidities for the amount of waters. We calculate the amount of water, and then finally we go and do a mass balance for N6. Okay, with N6 we got the Y fraction of I. Essentially we got all the balance, so we just need to find out mole V and total moles. So let's do it. This is kind of large, so it takes a lot of time. We need to be patient, guys. Remember the reactions NH3 plus 5O2 for NO. We're going to use it for our stoichiometry calculations. Plus, sorry, 4 molecules of ammonia react with 3 moles of O2 to do the incomplete 2 plus 6H2. So let's go up. Just let me tell you which one are which. We're going to use essentially this one here and this one here. Here. Now that you know which one is each, this one is 97% and this is 3%. So let's do mass balancing in NO. By stoichiometry, we know that 4 moles of NH3 will give me 4 moles of NO. So since we have only 97% of that reacting, so the 100 moles of NH3 essentially are 97. Check this. This number should give you 97. So 97 moles of NH3 are going to give me, of course, 97 moles of NO from here. Okay, guys? So let's do a mass balance in the converter on NO. You're going to get in minus outlet plus production minus consumption equals accumulation. No accumulation, no consumption, and no inlet, so we have essentially production equals outlet. What's the production? 97 moles This is N3. So we got our first mole flow here. Let's continue. Mass balance on the converter for N2, which is nitrogen. 3 moles of NH3 will give you 2 moles of N2. Let me go up. What are we doing? We are analyzing these 3% now. So the mass balance gets essentially inlet minus outlet plus production minus consumption equals accumulation. No accumulation. We have inlet, yes. I think we have the inlet of the air. Do we have outlet? Yes, we have the outlet. The production, of course, we have production. And consumption, I think we don't have consumption. Let's go up. No, we have no consumption. So let's take it. And from here we know that we're going to need a mass balance of air because this depends also on oxygen. So let's do a mass balance of air. And for that we need to do a mass balance of oxygen. So NH3 plus 2O2 will give me HNO3 from the past equation, guys. So we know that 1 mole of NH3 will give me 2 moles, or at least I need 2 moles of oxygen to have this reaction. So the 100 moles, I'm going to suppose it reacts completely by definition, so it's 200 moles of oxygen, the amount that I need. So that's the amount I entered in moles of oxygen. So this is N1, 200 moles of oxygen. Let me tell you why I used 100 and not 97%. Because they are mixing with the stoichiometric quantity of air. So even though you are only reacting 97%, you are mixing it. So even though you only need 97%, you're going to overdo this for 100%. You don't care, you just want to be sure that you're going to get 1 mole of ammonia for each mole, or 1 mole of ammonia for each 2 moles of oxygen. So that's why I use 100 here, guys. And yeah, essentially, I just calculated this here. Where is it? Let me go a little bit here. This value here, with stoichiometric relationship. And now we can calculate nitrogen 2, and then we can add the nitrogen 2. We are calculating this here. So even though this is from the reaction, just to let you know, this is the reaction and this is the actual flow. So sorry to mix you guys, but this is going to be changing. Okay, this is from the reaction, the mass balance from the reaction, and this is when you mix these guys, N2 and N3. Okay, so let's go further here. We were in this part, N1 equals 200 moles. Let's do the mass balance on nitrogen. How much nitrogen is that? So, 3.76 times N1 is the amount of nitrogen. So 3.76 times 200 moles will give you 752 moles of nitrogen. That's my flow of it. Now, what else can we do? We got this here, we got this here. We need to calculate this amount of water. How? With this humidity. So let's go back. Now, okay, by definition this is total pressure divided by the saturated pressure. You probably know this. Y equals humidity times the saturation and the total pressure. Humidity is 0.5. I found out this here in the book, so it's this here, and remember this is 30 Celsius, guys. The total pressure is 760. So once again, 1021. This is the amount of water. Once again, And this one goes as N of water times N of water plus NO2 plus N of nitrogen. So Y of water, it's equal to 0.021. And from here I got moles of water are 20.4, which is exactly the same thing I got before. Where is it? Here. It's similar, but not the same, guys. Okay, what do we do next? Actually, I think it's the same one. Just wanted to be sure if we do it by doing the mass balance on air and doing the oxygen and nitrogen balance. It's the same, that's good. You have proved that the amount of water is exactly this. So let's go to the mass balance on the converter. Once again in the nitrogen, I think I got that one before, yeah. This one, let's say it's number 5. Let's continue equation number 5. So that's number 5. We were about inlet minus outlet, gross production minus consumption equals accumulation. Now accumulation, not consumption, then inlet plus production equals outlet. Yeah, the inlets, it's 52 plus the production, we need to check that, guys, will give me the outlet. So for the production of nitrogen, I'm going to use stoichiometry. So 4 moles of nitrogen NH3 will give me 2 moles of N2. So what happens if we only calculate the other one? So 1 minus 97, this is the amount of ammonia that is reacting in this. So you see this quite slowly or with attention. You're going to see that only 3 moles of ammonia are reacting. Will give me 1.5 moles of nitrogen. So that's my production. Let's substitute here. Will give me the outlet. And what's the outlet? N4. So N4 equals 753.5 mole N2. Nice. Now we can actually continue with the mass balance on the oxygen in the converter. And this one is interesting because it's inlet minus outlet plus production minus consumption shall give me the accumulation. Now accumulation, and we're not producing oxygen, we are actually consuming it, so inlet minus consumption will give me the outlet. And the thing here is that consumption, it's consumption 1 by reaction number 1, consumption 2 by reaction number 2. So let me write this. The inlet is equal to N2. So N2 minus C1 minus C2 will give me the outlet, which is N5. And yeah, let me find these consumptions. 4 moles of NH3 give me 5 moles of oxygen, or I need 5 moles of oxygen. And the second one is, I have 97 moles of this. I will need at least 121 moles of oxygen. So this is consumption number 1. Let me write it before I get you lost. Consumption number 2 is given by 4 moles of NH3, give me 3 moles of O2. This is from the reaction, guys. Where I have it here, where did I have them? Okay, let's go all the way up. Here, guys. So look 4 to 5, and this is 4 to 3. So 3 moles of oxygen, but I don't have 4 moles. What do I have? I have 3 moles reacting. So the difference, 100, is the total minus 97 that I already reacted in the first reaction. I got 3 moles in the second reaction. So 3 moles of NH3 should give me a little bit less than 2. 25 moles O2. So this is the second consumption. Let me write it very fast here so I don't get you lost. And N2, what is it? N2, I got it before. It's, I think it's 200. 200, where is that guy? Here. These 200. Yep. Yes, that's 200. The amount of moles you enter of oxygen. So 200 minus 121 minus 2.25. How much is that? N5, 76.5 moles of oxygen. That's N5. Good. So we're going good, guys. I think let me just go find out how are we doing. We got N3, yes, N4, yes, N5, yes, N6, I think we don't have it. So let's do the mass balance of water. Mass balance on water in the converter. So classic inlet, outlet, plus production minus consumption equals accumulation. No accumulation, no consumption, we are only producing, so the inlet plus production equals outlet. N2, no, sorry. It's production 1. Once again, I think we're going to have 2 productions. And yes, look, 4 moles give me 6 moles of water, and 4 moles give me 6 moles of water. So we have 2 production concepts. Oh, this problem is going big. And yeah, essentially it's moles of water and 2. Where is it? Okay, where's it? N2 is what? So now I'm seeing, guys, that I told you it was N2, the amount of oxygen entering, and now it is wrong, guys. Actually, it's not N2, it's N1 here. Let me go. This is from the previous one. It's N1, N1. This is oxygen. N2 is it's water. So let me just show you where I got this 200 here. It's a little bit down. Yeah, here. These 200 moles is the one we calculated. So this is N1. And N water is different. N water is N2 here. So take care, guys. N2. This is N2. Let me show you a little bit. And I think we mixed. This is not N2. This is N of nitrogen. Actually, it's okay. Here I wanted to tell you this is nitrogen 2. And where else? This is N2 once again. Normally when you see N water is N2, guys. N1 is the amount of oxygen and oxygen. So sorry about that. The numbers are okay, just a little bit variable confusion, but we are doing well. These numbers are okay. It's the good thing to think and not just to write. Imagine if I were to write N2 and I were going to look for N2 and I don't have 200, I will be thinking, what the hell, I just calculated 200 moles of oxygen, where do I put those 200 moles of oxygen? So hopefully you are analyzing as you write your exams or your problems. You always need to think about all the numbers, where are going these moles, where are going to use them, am I going to calculate them later, or is it done? Always think, guys. Let's continue here. Inlet plus production equals outlet. The inlet, I told you once again, it's N2. Or let's use N water. Plus production. The production, I told you, it's P1 and P2. So from P1, let's do P1. 4 moles of ammonia will give me 6 moles of water. So 97 moles that go in the first reaction give me 6 moles. No, the equivalent, which is 145 moles. This is P1. And the same here, guys, actually, because it's the same stoichiometric ratio, will give me the same amount. So this gives me 6 moles of water. This comes from reaction 1. This comes from reaction number 2. This is the 97%, and this is the 3%, just to let you know once again. and I got here 4.5 mole of water. This is production number 2. So let me add these productions here, production 1 and production 2 equals the outlet. What's the outlet? It's N6. So N6, just to remind you, this is 20.4. N6 equals 170.4 moles of water. And essentially, guys, we're done. We got all these going out of the converter. We haven't calculated this. Actually, forget this. It was a comment, but I think it's going to confuse you more. And besides, we haven't calculated the recycle. So this is only this here. Let's calculate. Where is it? Yeah, here. Total amount of moles equals N6 plus N5 plus N4 plus N3. How much is N6? Is 170.4. N5, let me go for N5, where is it? 76 is here. 76.5 plus N4, where is it? N4, it's here. 753. .5 and N3, guys. Where is N3? N3, where is it? Here. 97 moles. Should give me the total amount of moles, which is in addition 1097 moles. That's the total. So we are asked to get the composition. Let me show you the composition. This is 97. This is 753. As always, nitrogen, it's a lot. Oxygen and water. So just divide by 1000. 97, 1097, 1097, 1097. And yeah, it's 0.088, 0.686, 0.069, 0.155. So this is letter A2. Your compositions plus all the mole flows here. Just relate here. And you're done with this problem at least at half, I think, because we are done with this and this. We still have to calculate 3, which I think is easy. Let's see how easy it's easy. And yeah, let's calculate A3. We need the fit, so let's do a mass balance in the condenser in the product line. So 4 moles of NO2 will give you 4 moles of HNO3. So 97 moles of NO shall give me how much? Also 97 moles of HNO3. So that's what I'm producing with this amount. This is N8. Let me go all the way up. N8 is this. So now let's relate to water. This was the mass balance. Let's do it in the condenser or in the process, the second process, hydration. Since in hydration we have no production or consumption in our inlet or outlet of HNO3, we don't need to do it for HNO3, but for water we need it. So the mass balance of water shall be 97 moles of HNO3. Is the 55% of that. So let's find the mass of this. This is in mass, and I have moles. Take care about that mole, this mass. So let's change that 97 moles of HNO3 to mass. I think this is the weight, and you get 611 grams of HNO3 or 6.11 kilograms of HNO3. Okay, now we got this is the amount of mass, so let me turn out to see how much is the total. So if this is the amount of HNO3 we're producing, and this is the 0.55% of HNO3, I want to know the total 1.0 of the mixture. So I just need to divide this. You should get around, let me calculate that, 6.11, 11.1, let's see, 11.1 kilograms of solution. And that means that 0.45 of that, it's water. We are doing the mass balance on water, so let me check that. I'll give you the amount of water. So times 0.45 gives me around 5 kilograms of water. Okay, let's turn that to moles. 5 kilograms of water, change it to moles. So I just need to divide by the amount of water. 18 kilograms of water, it's 1 kilomole. So divide this by 18, I got 0.277 kilomoles. But since I'm not talking in kilomoles in all my previous problem, I'm going to change it to moles. It's 277 moles of water. And what's this? This is essentially these guys, N9. We just found out N9. N9 equals 277 moles of water. Good. But we need to find out how much are we adding, not how much are we producing here. So if we do our mass balance here, we know the water, but we need this here. So let's do a mass balance. Mass balance of the hydration phase water. So give me the inlet minus outlet plus production minus consumption equals accumulation. No accumulation, no production, no consumption on the inlets and outlets. Let's account for each inlet. The inlet is N6 plus N7. The outlet is N9. So let me go for and show you where is N6. N6 is the amount we produce here, and the amount here is N7. So probably are you asking yourself, where do we find out this recycle? This is not going mixed, this is only a heater. It enters and it goes, so it's the same composition, they never mix. So this here is exactly the same as this composition here, and this composition here enters this hydration phase. So hopefully I didn't mix out. Actually here you can see how the line goes, means doesn't mix and goes out. This only goes here, this is heating per process and not mixing per process, so take care about that. Hopefully you got that. It's N6 plus N7. N6 comes from the reactions, N7 comes from the cooling, we're adding the liquid, and N9 is the resulting or the final addition. So N6, how much is that? It's 170. And N7, how much is that? I don't know. That's what I want to know. N9, I just calculated here, it's 277. Sorry. So let me show you N6 before N6. How much is N6? Here, look. I'm not lying to you, 170. And N7 goes as this. It's about 107 moles of water. And they want it in volumetric flow, and since it's a liquid, please don't use ideal gas, use densities and mass relationships. So I know that the volume equals the mass flow divided by the density. And I don't have mass flow, I have moles, so how do I relate that with molecular weight, of course? So the mass flow it's 100, no, the mole flow it's 107 moles of water times the molecular weight, which is 18 grams per mole, and the density is 1000 kilograms, and since I'm using grams I'm going to use grams. It's 1 gram per milliliter. Let me do this. It's going to be 100. We got 1926. Moles goes out with moles, grams with grams, and I got milliliters. But I don't want milliliters, I want cubic meters. So just divide that into liters. Where is it? Okay, liters will be 0.19, 1. So this amount will be in liters, 1.9 liters. But I don't want that. I want cubic meters, so 1.9 liters. Let's change it to cubic meters, which is a little bit less. 0.0019 cubic meters. That's my volumetric flow of water. And we're done, guys. Finally, we're done with the mass balance. We just need to do this scale up the results to a basis of 1000 metric tons of nitric acid. So let me do that for scale up. We need to find the scale up factor, so the production will be N8 plus N9. This will give me moles. And yeah, essentially it's 97 times 277. This is 374 moles. I need to find the molecular weight in average, so it's now let's go directly to calculate the total mass flow of product. It's 98 times molecular weight of 8, I think is the HNO3, plus the N9 times molecular weight of the water. N8 is 97 moles of HNO3. Molecular weight is 63 grams per mole of that, plus N9, which is 277 moles of water, times the 18 grams per moles of water. Look how they cancel, and I'm going to be able to add all the grams. Grams are going to be 100.1 kilograms, which makes sense. I just wanted to assure that this amount was correct. Where is it? Just calculated 11. Oops, I don't find. Yeah, here. 1.1 kilograms of solution. I just wanted to be sure that the mass balance was done right. So yes, it's done right. So let's continue. We have that, and let me calculate the factor. Factor is always the mass design, the mass flow of product for the scale up, divided by the mass flow of the product previously designed. So we went, or they want 1000 ton of that. I will have 1.1 kilogram. So let me change this kilograms to ton, and we will be able to calculate the factor, which is it's a lot, 90, 0.90. That will be our factor. So let's go and answer our questions. The good thing is that it is linear. We don't need to do the mass balance again. This is A1, A2 will be V of air, which was, I don't remember it. Let me go up, N of air, volumetric flow of air. Where is it? Where is it? Where is it? Here, 24.2 cubic meters. A2 was B of water. So I'm scaling all up. So okay, have this, and I think it was 0.0019 cubic meters. Let's just multiply all these times my new factor. And it's 24,504 cubic meters. 22,180,000 cubic meters. And this is 171 cubic meters. That's my scale up. So we're done, guys. I know it was kind of large procedure and too big problem, but it's good. So let me give you a conclusion. Let's see how you understand the problem. Hopefully, look here. This is only air in the recycle. There is actually no recycle. You just go here, you preheat, and it's everything. This amount here is the same as this amount here. So the first thing we did is the diagram. The diagram is very important to do because if you don't do it well, you're going to have problems. For example, this, since the beginning, I told you that we were not going to need that. And yes, good, we didn't need it because it's unnecessary. What else do we have? We choose this fit for convenience. We started everything from the saturation data, so you do not know what about saturation. You wouldn't be able to start your mass balance at all. So the strategy at the beginning to get the volume was to get the temperature in which it's saturated, use Antoine equation, and calculate the C. Once we got C, we calculate the volume. So we found out how much was C graph here. We continue and we got the total amount of volume here. That's the first thing they asked us. Then they wanted to know the volumetric flow of air as ideal gas. Once again, the strategy was get dry air, get water, mix them, and change them to volumetric flow, which is here. The total amount of water plus the total amount of dry air will give you the total amount of the mixture. And we use ideal gas to get that. And finally, the Mosley converter is kind of tricky. You need stoichiometry and account for that 97% of conversions. And then here get the mass balance. Actually, this is just mass balancing everywhere. And finally, once you got all your mass balance, get the total amount of moles and the composition. So this is the reaction number 1 we used, and reaction number 2, which is the one that only goes or consumes 3% of the initial moles. We did some mass balances, inlet, outlets, productions, consumptions, etc. until we got, you need to take care in accounting double consumptions when you have the same reactant or product here, also here 2 products. We continue and we got at the end all the mole flows out of the converter. You add them and it's 1000 moles. Then I calculated all the compositions. That's easy. When you have all the mass balance, this is super easy. And finally, we did this, which is calculate the amount of water we are using, and I got this one. You actually just need to do a mass balance, molecular weight, and density of water to get that. And the scale up, I think, is the super easiest one. Once you have all the mass balance, scaling up and down is easy. So just got how much water they want me to produce. I had a basis of 11.1 kilograms. They wanted 1 ton, which metric ton is 1000 kilograms of 1000. And yeah, essentially I got this factor, which is a lot, which makes sense, guys, because 11.1 kilograms, nobody wants that. That's too low. So yeah, we got that. And the factor is this. I wanted 90,000 times more what I was calculating. I got all these and we're set and all done. One note I want to tell you is that I have no, for example, I use emp dot and n dot, which means mole or mass per unit time, but I never choose a unit time. As you see here, I use 100. So this can be done for 1 year, 1 day, 1 second. You just need to write the unit. So that's an advantage also. You can scale up or scale down for time, not only quantity of mass or mole. And yeah, essentially it's everything, guys. See you in the next problem, which will be also very interesting. We're almost done. We're on the half of the problem of this section. So take care and keep practicing, guys.